Okay, so welcome to the class, and let's go with the stuff. So counting continued, right? Like counting 10.5, 10.6, 10.7. That's the kind of counting we mean here. So we went over these processes last time. What we have, so I'm not going to go into depth here. The point is, we know how to count sequences of length n over certain alphabet with no constraints, and we also know if there is a constraint that there should be no repeats, then that thing is called R permutation, and we know how to count it. And if there is unordered and no repeats, then that's a subset, and counting subsets is just n choose R. And we also have these rules that are basically can kick in at any moment. If you perhaps basically they allow you to count something that like does not fall easily into these, but it can be mapped onto something that does. Okay, so let's look at some examples that come from poker. So it's like why poker? Because it's sort of complex enough and yet simple enough that it gives rise to nice counting problems, essentially, right? I mean, and of course, the goal is not to encourage you to gamble, but to learn how to count, and these would be mapped then to some problems that you encounter in other realms than poker. Okay, so poker, you have 13 cards, you have 52 cards divided into 4 suits: diamond, hearts, clubs, and spades. And the cards are ordered from, you can order them from ace to king. Another ordering is 2 to ace. It doesn't matter. Ace, jack, queen, and so this is jack, queen, and king stand for jack, queen, and king, and ace are figures. 2 to 9, 2 to 10 is numbers. And each card has a suit and a rank. So there is an 8 of diamonds or queen of clubs. And each of these is unique. There's only one in the deck. Okay. So each rank suit combination is possible, and each one appears only once. Okay. Sorry. So okay, great. So there was a problem in connectivity, but okay. So let's say, okay, here, when you play poker, you draw a hand from the deck. So the deck has 52 cards, and you draw a 5-card hand. That's called hand because you keep it in your hands. And in the subsets that you draw, the order doesn't matter. You can order them any way you want locally. So it's just draw basically a subset. So therefore, the number of choices is 52 choose 5, right? Because these are just subsets of the 52-card deck. But let's say that you ask, how many hands are there that have some constraint? For example, exactly 3 clubs. So in a poker context, constraints are scored. There is ways of scoring. So if you have a 3 of some color, that's a figure in poker. So like that gets you certain power of the hand, and now you can negotiate and win money, right? And but we are not concerned with that. We're just concerned with like, okay, here are the examples of constraints, and we want to count them. But being able to count them, of course, translates into probability with which a random hand has that figure. And if you play, this is important because like that will give you probabilities of what other players can have, right? And or what you could possibly have if you change cards. So, okay. So the constraint says you have to have 3 clubs. Okay, and now what? Okay, so how would you divide the process of choosing a 5-card hand with this constraint of 3 clubs? Well, how about spreading it into two processes? First process, choose 3 clubs. Second process, choose 2 among the remaining suit, right? Because 3 clubs means only 3, not 4, not 5. Yes. So one process is just choosing 3 clubs from a set of 13, right? And the other, so you have a 13 choose 3, and the other chooses the remaining 2 out of the remaining suits. So you have to remove all 13 of clubs, and then you have, 3 times 13 of the remaining suit, right? And because these are 2 different processes, right? One choosing clubs, one choosing the remaining 2, you multiply them. It's a product rule, right? It's an independent choice of clubs. Is independent from choice of non-clubs. Okay, let's say here's another constraint. It's a figure in poker called 3 of a kind. That means that means like 3 queens. So it's separate, like rather than same suit, you go same rank. And it doesn't matter what suit they are. They can be 3 queens of, club, spade, heart, right? And it could be 3 of any color, any rank. So it can be 3 2s, 3 3s, or 3 4s, etc. 3 aces, 3 jacks. And it's not 4. So 4 is like yet another figure, okay, which I forgot what it's called in poker. It has some special name. So now what's the division? Okay, how about this? One process chooses which rank you're gonna have 3 of a kind. Thankfully, there's 5 cards. So if there's 3 of a kind, then the other 2 cannot form a 3, okay? So that actually simplifies counting, because, so what's the characteristic of a 3 of a kind hand? Specification of the rank that you have 3 of. So that's going to be a process that is independent of everything else. So it's 1 out of 13. Then there is a process that's going to choose particular suits for these 3. So it's a choice of 3 out of 4 possible suits. And then there is a process that assigns the remaining 2 cards. And how does he assign? It has to be remaining 2 cards from other ranks. Okay, and these are independent. So this is funny that it's independent, because of course, if you set the suit, the rank here, then these 2 cards are chosen from other ranks. So it's dependent because you're choosing them always, but you don't have to. Somebody can just choose 2 numbers from a set 1 to 12, completely in the right, from a reduced 1 to 12 alphabet instead of 1 to 13. And if the person who does this first process chooses the rank, then this choice of 2 indexes in the range from 1 to 12 is going to be mapped into proper cards, because right, because, or now actually, yeah, it's maybe not 13. Okay, I messed up. It might not be just a choice from a rank of these cards. It's a choice of the actual cards. So it's actually not from 13, it's from 52 minus 4. Once you settle these cards, the 4 cards of this rank that is now forbidden in this process. Okay, so choosing the rank is choose 1 out of 13. Choosing the 3 cards within the rank is 4 choose 3, which is, so you have 4 choices, right? Because it's like you just choose which one is missing, and there is 4 possible missing suits. And the 2 remaining cards are all cards minus these 4. Yes, minus all cards of this chosen rank. Yes, so I said badly that you're choosing 2 indices out of in the reduced set from 1 to 12. You're choosing 2 indices in the reduced set from 1 to 52 minus 4. right? And it will be mapped onto the full deck once you remove, once this person chooses which rank to remove. Okay, so in that sense, these processes are independent and they are going to map to a unique choice of the card with this constraint. So therefore you can just multiply them. Okay. Perhaps this is not so hard to see, but okay, there is like a moment here where you have to sort of convince yourself that this choosing is really independent of defining which rank is going to be missing. Some rank will be missing, exactly one, and you don't have to know, and you can choose the other cards in this way. Or another way to think is like this: let's just do them one by one and do this thing last. In that case, it's clear that you're choosing from 52 minus 4 cards. Choosing these two from this remaining set. Okay. How about 5 card, a hand that has exactly 2 pairs? Now that's more complicated a little bit, because the choice of a rank, for one pair and the choice of the rank for another pair are not, they're not independent. So once you choose a rank for one pair, then there is still a possibility for another, right? So let's be more careful here. Let's do this, I will still argue that these are independent, but let's do them one by one in sequence, because it's easier to see. So you first determine which 2 ranks are, what's the rank of the first pair, what's the rank of the second pair. Then you choose 2 suits. One, where first you have to choose the 2 suits that you have 2 ranks that you chose, right? You can order them. There's a lower rank and a higher rank, always. Let's separately choose which suits will be these 2 cards from the lower ranked pair, what suits they will have, and then the second process will choose what two suits will be of the 2 cards in the higher ranked pair. Why do I insist on this division, lower rank? Because I have to be clear that there is a separate process that can be applied to this and a separate process that can be applied to this. And then these 2 processes are independent and are always well defined no matter how you choose these, because there is always going to be the lower one and the higher one. If you don't get this quite right, you might overcount by a factor of 2. You might think that you're choosing each of these ranks. The problem is, are you taking this 2 in an ordered way, or are you thinking them of unordered way? Because the first thought is take them unordered. I just need 2 ranks. Who cares which of the 2 ranks I chose first? But then the process is here. Well, if this process counts how many possible suits are of the rank that you chose first, and this process counts of the rank that you chose second, then what happens if if one guy chooses queens first and jacks second, and the other takes jacks first and queens second? You're creating the same set of cards in this way, and you're overcounting them. And then choose the remaining cards. So I will choose this set unordered. Doesn't matter which one was chosen first and second. But then once I do it, I will still have a notion of an order between them, but it will not be about like which one was chosen first, but which one is lower rank, because I need this process and this process to be well defined. And each of them is just 4, choose 2. And the rest is easy, right? Because I reserved now 4 cards of one rank and the other rank, and they're out. The remaining 2 cards have to be from the remaining cards, right? So I actually removed 8 cards from the choice of possibilities for not remaining 2 cards, remaining 1 card, right? The one that is in neither of these 2 pairs. So this is a subtle point, but this is the reason. If you think of this as a sequence, you're going to overcount by a factor of 2. Okay, and now they are independent, and you just multiply them, right? This is a subtle point. It gives people a lot of pause, so don't worry if it does. But you know, let's take it on Piazza. If this seems like a weird way of counting, okay, there's something off in this way of counting. So okay, another constraint. There is no figures, okay, or otherwise called first cards. So that's easy. You just choose. So the cards are just numbers. So you're basically choosing from a reduced alphabet instead of reduced set, right? Instead of all cards, you just kick out all the figures. So you have only 9 cards in each suit, so you have 36 cards. Okay. How about, okay, this I'm going to skip some other example. You know, just you can see it on the slide. There is more of these counting problems, you know, in the textbook. So like just you know, get your counting you know, motto, I think is the word. I don't know if I'm pronouncing it correctly, you know, by just practicing. And I will also post a final homework, which is basically just a review of these counting problems from the later part of the chapter 10, right? So you also need that to prepare for the test, obviously. Okay. Another counting. So, and what does this also practice? What it practices is how do you divide a counting problem into clear processes? Is it the sum? Is it the product? How do you make sure that these counting decisions are independent and that you count them correctly and that you leave off the rest, and what you get in the end is exactly the sets that satisfy a constraint, no more, no less. Yes, that's what it is. That's the point of all of this. So here's some examples of counting by complement. Okay, we have seen this when we said that, look, when you count subsets, all 3-element subsets of a 10-element set, you can just as well count all 7-element subsets of a 10-element set because they are complement of one another. So every choice of 3 corresponds to, can be represented as a choice of 7 that you don't take, which these two are counting of complements, and they gotta be equal, right? And this is why n choose r is always the same as n choose n minus r. But let's see more cases of that. So let's say you ask how many 5-card hands have exactly 1 club. Okay, that's easy. That's a case of what we've done before. Choose the rank of the club, 13 choices, and then choose the 4 cards from the remaining 4 cards from the rest of the deck, which is that you remove all the clubs. So you only have 3 other suits now. 3 times 13. Choose 4 cards. Okay, so far so good. But let's say that you have at least 1 club. Well, so now you can divide the space into 5 disjoint possibilities. I take exactly one club, then I count it as I did on the previous slide. Let's consider hands which have exactly 2. We had it on the side, exactly 3, exactly 4, and then I guess exactly 5. But you can see that this is somewhat an onerous way to count, and for more complex problems like this, basically, like it doesn't, there's some sort of nasty formula that is not an efficient way to count. Here is exactly the thing that complement works very well, because let's say that you're counting you have a universe of items, let's say decks, hands in a deck, right? All possible hands. But then you have a subset, P, such that perhaps it's hard to count, but you can look at its complement. And then you know that if you can count how many are in the complement, then you will have an easy formula. You'll take everybody in the universe, all 5 card hands. You will remove, just subtract all 5 card hands in the complement, and then you will get the 5 card hands that you care about. What's the complement of 5 card hands with at least 1 club? It's easy. It's 5 card hands with 0 clubs. That's the only thing, and exactly the thing that is in the complement of the set. And these are easy to count, right? The 5 card hands with no clubs, it's very easy. You just take you choose 5 cards from all suits except of clubs. And of course, the whole universe is all possible hands. So 5 out of 52 out of all the deck. And that's it. To a much faster formula than than what I had on the previous slide, which I didn't even give you the formula, but you could sort of derive it, but it would be more complicated. So as 1-to-1 or K-to-1 rule, counting by complement is just something that kicks in, where if you've seen examples, you'll be like, oh, that's a tricky thing to count. That's unpleasant to count. Is there some faster way? Oh, complement is easy, good. I'm fine. Okay, and you just have to see a bunch of examples where like this kicks in, so that you can maybe remember that's a quick way, sometimes useful. How many 8 passwords of length 8 chosen from this alphabet? So all the characters just ABC, okay, limited alphabet. And they have at least 1A, okay? Again, you can enumerate all the possibilities of 1A, 2A, 3A, but that's annoying. Much faster, just look at all characters from the complement. What's the complement? It's all 8 character strings over this over-reduced alphabet. Just kick out the A. And so this is easy. How many characters over the 3 character alphabet? 3 to the 8. How many strings over alphabet with 2 elements? 2 to the 8. And that's your answer. Okay, here is yet another counting problem. Counting permutations with repetitions. Okay, what on earth is this beast? Permutations with repetitions. Here is what I mean. So we have all these processes. I'm not going, but look, we know how to count ordered sequences where there is no constraints. You can repeat elements of this characters from this alphabet, put them on different positions. It's fine. If you have no repeats, we also know that's an R permutation or T permutation in this case. What about if you have unordered elements where they're just counting subsets? There is a natural counting questions which corresponds to ordered selection. and they fall between these two cases. Repeats are allowed, but they are limited. Okay, and now the whole question is, how limited? What is that? In what sense? Okay, let me give you an example. You have 3 characters bad, and you want to count how many permutations they have. Okay, well, 3 factorial. Now, what about these letters? ADD, right? These are the 3 permutations because these 2 letters are identical. So any permutation of D and D doesn't count as a permutation. So it's like as if I had all of these, but then I made B and D equal. Then in that case, bad and dab would be the same thing. And BDA and DBA would be the same thing. That's actually going to be helpful in counting these. But you can see that this is a different process, right? And to generalize, what's happening is that you're choosing order sequences, and you're choosing them from this fixed set. But you have exact limits on where, so repeats are allowed. It's as if you had a bag here with a bunch of A's, bunch of D's, and that's it in this case. And there is exactly 1 A and there's 2 D's. So A has to repeat once, I mean 0, and has to occur once, and D has to occur exactly twice. So that's the notion of limited repeats. There are just every character has a exact budget for how many times it has to occur. Of course, this would be even more complex if you were shown that were told that D can appear from 2 to 4 times, but we don't do that now. So what's the general rule? So let's reconstruct the general rule from a specific example. So let's take Mississippi. In other words, you have 11 letters divided into groups of 4 types, M, I, S, and P. And you're given exact budgets. M has to occur once, I 4 times, S 4 times, P twice. So how do you count? Well, you can, how would you count? Like this. Choose one of them, no matter what order. Okay, I'm going to pick some order and just run with it. So let's choose I first. And so in that 11, I know that my string has to have 11 characters because the budgets are set. I know how many strings occur of every character, therefore I know the whole length. So I have 11 positions, from which 4 of them are going to be I's. So I choose the positions where I place the I's. Now I choose positions where I place S's, but I already placed I's somewhere. It doesn't matter where I place them, there is a well-defined sequence of 7 remaining places, remaining indices. Out of those, 4 of them are going to be occupied by S's. And then I repeat. So for P's, there is 4 places taken by M, I's, 4 by S's. There is 11 minus 8 remaining positions, of which I choose 2. And for M, there is no choice, right? I mean, if you wanted to extend it, it would be 11 minus 10, choose 1, which is 1, choose 1, which is 1. So the total is this. So these processes are sequential. In fact, they're, like you can render them as independent, but whatever. You can think of them as sequential. It is easiest to think of them as sequential. But the only thing that matters is that this process doesn't care. It always has this range of choices, no matter what choices were made by the previous process. You're always choosing from this range of possibilities. Okay, the exact indices might be different in play, but there is 7 of them and they're well ordered. It does not matter how this process came out. Okay, but doesn't this formula depend on how I choose these? You know, if I started with the placing M and then placing P's, I would have different combinatorial factors here. I would have 11 choose 1 for choosing the M. If next choice was P's, then I would have 10 choose 2. And then I would have 8, because three places are taken, choose 4. So a very different stuff. And at the end, I would have 4 choose 4, which is 1. So is the final answer depend on this order? Of course not. But here's the why, right? So this is the total. And if you now let's look inside. So 11 choose 4, that's 11 factorial over 4 factorial times 7 factorial, 11 minus 4, right? 7 factorial. So 11 n choose r is n factorial over r factorial times n minus r factorial. If I do this here, I get 7 factorial 4 and then 7 minus 4 factorial. And likewise here, 3 factorial 2 factorial, 3 minus 2 factorial here. And if you see this and that cancel out, this and that cancel out, and what you get is this. And this will always, no matter how you order them, because how many are you in this process? What is this number? It is exactly n minus r of the previous process. If there were n spaces to begin with and you chose r of them, the number of spaces you're choosing now for the next letter is out of n minus r. Therefore, these two will guarantee to be always the same, no matter how you order these. Right? So in general, and what did you get in the denominator? 4 factorial, 4 factorial, 2 factorial. Is that a coincidence? No, because here you choose 4. So this factorial is not going to cancel out. And here you were choosing 4 again. And here you were choosing 2. So these are the factorials that will not cancel. It's the n minus r that will cancel with the next n, so to speak. So in general, if you have a process where you have some characters and you're exactly told how many copies of each character there needs to be, let's say that the total number of characters is n, right? So there has to be R1 copies of the first, R2 of the second, etc. The formula for counting how many arrangements of these characters there are that satisfy this constraint is this. Is the way of ordering all divided by the all possible sort of inside orders of these characters. Okay, that's the formula. And it's a generalization of, you see this as an example. If you reorder these and do the counting, you will see that you will come up with the same. Okay, there is another way to see that this has to be the case. Okay, so I have a Mississippi example exactly here, right? As in on the previous page, it is a case of this where my multiplicities are 4, 4, 2, and 1, and so this becomes this. But it is a case of a K-to-1 rule. That's another way to convince yourself that this has to be the total number of choices here. Because here is how to see this as a case of a K-to-1 rule. The K here is this, this expression. Here is how to count all these objects, okay, all the permutations of these objects. let's pretend that all CIs, like I's in this case, where the C1s, that all of them actually have a little marker that says, I'm the first, I'm the second, I'm the rth. Okay, so as if these I's have a little marker. There's a first I, second I, third I, and a fourth I. Let's pretend that S's have a little marker. There's 4 of them. So first S, second S, third S, and fourth S, and so forth. If I pretend that each of these letters have a little marker, then they become unique letters. So there will be n factorial ways of ordering them. But the markers were just, in my head, right? Like when you permute these letters, there is no difference between S's. So I have to remove the marker. That's the F function that takes a permuted string which over n different characters. These are letters with little markers that make them unique. That's the space of all permutations if you pretend that the letters have markers. So there's n factorial of these. But if you now make this F function makes an action, remove all markings on these, the pretense markings that made all I's distinguishable, all S's distinguishable, and so forth. If you remove these markings, obviously you collapse different, right? Because all permutations with I's of different marks, that first I, second I, third I, fourth I, or perhaps fourth I, second I, third, and fourth, if they were in the same positions, they are going to map to the same string. If the function f just does the following, it loses this marking. But how many did it collapse into one spot? Well, as many as there are permutations of these 4 marked I's, which is 4 factorial. And it did the same with S's by losing their markings. How many permutations of S's there are inside that it lost, this function lost? 4 factorial again. In general, if you are collapsing all inner permutations of R1 of character C1, you're going to lose far1 factorial are going to be mapped to the same thing. And the same for all the other characters. Therefore, this is the loss factor of this function that takes permutations of letters with little markings to permutations that lose markings, and that in which every occurrence of S is indistinguishable. So this formula, here is the way to see it, because you can do this in general for any, you can make it n, R1, R2, R3, R4, and these cancellations of n minus R1 factorial and n minus R1 factorial here are obviously canceling. This one will be n minus R1 plus R2, and this one will also be n minus R1 plus R2. They will cancel, and all you're getting here is R1 factorial, R2 factorial, R3 factorial, etc. But you can see the same thing being true without resorting to these exact arithmetics, and right, you can see this as this case. And it's a very natural case of just pretending the letters are marked and then losing these markings. Okay, so an example, how many strings of this alphabet ABCD have exactly 6 of A's, 3 of B's, 2 C's, and 7 D's, and we just plug it in, right? Because why 18? Because if you take 6, 3, 2, 7, you have 18 characters. So that's how long your strings are, and so you have 18 factorial possibilities, if they were all distinct, and then losing the overcounting caused by the fact that this would correspond to A's that are distinct, but they're not, is 6 factorial. the overcounting of pretending that B's are distinct, but they're not really, is 3 factorial, etc. So again, I'm explaining the general formula again, rather than just using it to stress the point. Okay. Yeah. Okay. So here is another case. Let's say you have 20 tasks and 5 computing agents, which are students, and you want to assign tasks to students so that everybody has the same number of tasks. Very natural problem, right? And you can think of this in different ways. You can see, okay, am I assigning students to tasks or tasks to students? It will be very different interpretations of the problem. It's not like one of them is wrong. As long as it is a correct interpretation, you might get there. But some of them are easier than others. So if you have trouble counting in one way, try to change what is assigned to what and see if this doesn't make it easier. Here, an easy way, it will be when you realize that that numbers of assigning these 20 distinct jobs. So the 20 jobs have to be partitioned among these 5 students, right? And well, how about we have little letters for students? Student A, student B, student C, student D, student B, and student E, and we just throw them into the string from 1 to 20. This would be the task. So we take students and we put them onto tasks. And we know that each student is going to get 4 jobs exactly. So we're going to have 4 letter A's to represent the jobs for the first student. And we're going to place them somewhere in this 20 character string. And likewise, we'll have 4 letters for the student B, and we'll place them somewhere, but on different locations. So an assignment in this representation will be a 20 character string with exactly 4 A's, 4 B's, 4 C's, 4 D's, 4 E's, right? Perhaps there is another way of rendering if you flip who is choosing, who is the one who is choosing whom here. But if you do this one, it's a case of the the problem that we were right, because now you see it's like Mississippi, but with 4 of every, and with 5 characters, and multiplicity 4 of every one. And right, so an index of A in the string will be telling me which job the student A gets, and the indexes where I place B's will be which jobs student B gets. And so therefore, this formula tells you it's 20 factorial divided by all these inner permutations of A's, B's, C's, and D's, but because each of them is 4 characters, so it's 4 factorial. So therefore, it's 4 factorial to the 5th power. And that's your counting formula. If you try to sort of think of the, having some characters representing the job and placing them in something that is like student character, that might get you there, but it might be more difficult. Post on Piazza if you see a different way of counting this. But here's one way, which immediately applies the formula we just we just went over. Here's another example, 10 cookies to 10 kids, such that each kid gets a cookie. So, right, because you have 10 cookies and 10 kids, but some cookies are the same kind. There's a 3 of chocolate chip, 1 sugar, 4 ginger, 2 oatmeal. So within the variety, you don't care which oatmeal one you get. Just like in the Mississippi, there's 2 peas, and you don't care which position they are at because they're identical. So these are, you have these letters, and you're choosing a permutation of them. This is what the first kid gets, this is what the second kid gets, etc. Right? Like if this is the permutation, but there is 10 characters, but it's not 10 factorial number of orderings, because some of the characters are identical and equivalent. So you have to divide them out by these equivalence classes. Anyway, I'm explaining the formula again. It is the same formula, just using a different language to express it, because I believe that might be helpful. I'm not sure how many examples I have. Okay, this is the last one, and I'm running out of time. So, but how many ways to distribute 20 different books to 10 kids if each kid gets same number of books? Again, this is basically like 20 problems, 20 tasks to 5 students, where the multiplicity must be the same, right? So it's like a 20 character string with now 10 characters, each one with the multiplicity 2. Okay, so it's 20 factorial over 2 factorial to the 10th, right? It's exactly like this assigning students to tasks, but there I have 5 students and 4 multiplicities of each. Now I have 10 students, quote unquote, and 2 multiplicity of each, right? Because each kid gets 2 books, right? You have to see what's the multiplicity. It's not explicitly stated, but obviously if you have 20 books and 10 kids, each one gets 2. But if you didn't have restrictions, okay, so this will be a typical thing. We give you something that is difficult to count, but then there's like easy versions, right? Like if you don't have restrictions, then suddenly this becomes a much faster formula, right? And you can see of these variants and sort of walking through the space where some versions have very fast answers, but okay, of course, once you see them, and then others will have more complex answers, right? Okay, that's all I had for today. Luckily, because I'm slightly over time. And if you have some questions you want to ask, go ahead.
Professor?
Yeah.
For this last problem, because you only have 20 books, wouldn't it just be a permutation of 20? For the last one, instead of 10 to the 20?
No, that's why not, right? Because if I permute 20 books, and I say, let's say I say the first 2, the first kid gets, the second 2, the second kid, so books, when I permute 20 books, and I give first 2 to kid A, the second pair to kid B, third pair to kid C, etc. I overcount, right? Because the inner permutations of which book became first and which second does not matter. Both of them go to kid A. So that's yet another way to see that you can order this way. Thank you, because it's a different way of thinking it. Permute the books, but then realize that the first 2, the inner permutations between these 2 characters don't matter, because the first 2 go to kid A anyway. So you take permutations 20 factorial, you divide them by a 2 factorial of loss, k to 1 function, because the inner permutation within the box that represented kid A don't matter. Do the same for kid B. It had 2 books in it, and the inner permutation of these two books for kid B didn't matter. So you have to remove 2 factorial for kid B, and you have to remove 2 factorial for each kid, because so that's very good. It's a different way of thinking, which eventually gets you the same thing. Take the books, permute them, think of buckets 1 to 2, 3 to 4, 5 to 6, 7 to 8, etc. as kid A, kid B, kid C, kid D, and then do the K to 1 function by killing off the inner permutations within the buckets. There's going to be 2 factorial to the 10th of loss if you do the K to 1 function that removes all these inner permutations within buckets.
Okay, I think I get what that means. So basically, you're saying that the order doesn't matter, or the order.
Well, I mean, if you want to think of this as you totally can. Permute the books. Think of kid A as the first 2, kid B as the 3rd and 4th, kid C as 5th and 6th, etc. Call them buckets, and then remove the permutations within buckets.
I think I get that, but I think we're talking about different problems. I'm talking about the one that says how to distribute 20 different books to 10 kids without the restrictions on number of books per kid.
Oh, without the restrictions.
Yeah.
Oh, sorry, I thought that you were thinking about this.
Because once you give
oh my goodness, yes. No, wait, no.
It becomes a weirder question because
no. Yes, hold on a second. So I have 20. Hold on, I have 20 books to 10 kids. No, it's like hold on, a string over the alphabet of kids. I can give, A means all the books go to kid A. A, and then a bunch of B's means, the first bunch of goes to kid A, and no, so these are strings over the alphabet of 10 of length 20. Each such string corresponds to a different assignment, and every assignment is like this. If you permute the books, this is a constraint. 1 book per kid.
Yeah.
If you just do 20 factorial, that means that's a correct answer to a different problem. It's a problem. I have 20 books and 20 kids, and 1 book gets to 1 kid. Mm-hmm. Every kid gets a book. Yeah. So if the question was, I have 20 books, 20 kids, each kid gets a book, that's 20 factorial.
So how do you get the 10 to the 20 then?
Because it's a different problem. Because I'm taking 20 books to 10 kids. Do you have a phone ringing? I'm sorry, I have to. I have a phone ringing. Okay, it died. So, okay. I have 20 books and I give it to 10 kids. Are you saying this is the wrong answer?
Oh no, I'm just wondering how you got there.
This is how I got there. Every assignment I represent with a string of length 20 over alphabet with 10 letters. Every kid has a different letter. There is a kid A, kid B, kid C, etc.
Oh, I see now.
And I just make a string of these letters. Whatever letter I chose first, that's book 1. That's who gets book 1. Whatever letter I chose second, that's who gets book 2.
So it doesn't matter that once you give up a book, like the way you're solving it is that you're assuming that each time you give a kid a book, you always have 20 different books.
No.
Oh, because isn't the pool going to be smaller to give from every time you give a number of books to a kid? So if you give
yes,
one,
but I'm not doing it this way. I'm not hold on. But there is always like book first. Okay, so first I order books. There's a book 1, book 2, book 3, book 4, and book 20. Okay, so let's represent them with as indices: first, second, third, fourth, 20. And now I'm choosing which first index, first book, which kids gets it. I have 10 choices. The second book, which kid gets it? I have 10 choices. Third book, which kids get it? I have 10 choices. So it's 10 times 10 times 10 times 10.
Okay, that makes sense
20
now.
times, right?
Yeah.
That's exactly the same. I have 20 spaces, and I have to put any character in these 20.
Okay, I see it. So if you, yeah, I see it.
Any kid gets. Yeah, so I think of them as characters because this is the natural from this perspective, right?
Yeah, that makes sense. I think I just was perceiving it from a different perspective. I think if I put my perspective in the books, it makes more sense. All right, thanks, Professor.
Okay, thank you.
On slide 7 of this presentation, I had a question on your step 3.
Which slide?
Slide number 7.
Oh, you know what? I don't have the numbers.
Yeah, so on step 3 over there.
Are we on the same page now?
No, slide 7. So it's the one with the 5 card hands.
Sorry, because when I do a slide presentation, I don't have page numbers, so I don't know which page this is. Let's do this. Okay. Now I have the right one, right?
Yeah, okay, that's the right one. So for step 3, you're saying choose 2 of the remaining cards, right? So how can we have 52 minus 4? Shouldn't it be 52 minus 3? Because you've chosen 3 of the cards?
But no, I have to remove all the cards of that kind. Because if I didn't remove all 4 cards of this kind, I chose only 3 of them, but I have to remove all 4 of that kind, because
that makes
sense. I chose another one from the same kind, I would get 4 of a kind.
Yeah, okay. That makes sense. Thank you.
Hey. When I did this, I lost the chat. So if there is somebody asking something on the chat, please just speak up. Okay. So I take it that there's no questions. I will put these slides online. I noticed that I forgot to put the Wednesday lecture yet. So I'll put both of them, and also send you another batch of exercises so you can. I mean, they're all open, but like I would just choose them and send it to you right now. Okay. All right. Thank you, everyone. Thank you, everyone. Have a good weekend.